Home stretch here today and one more lecture. A few announcements relating to the assignments now that I have a view of how far we'll get through the material. So problem set 1, which was past due now, is due on Tuesday, but it's a nice relaxed grad course, so we'll still take them late if you want to buck up and give them a shot. In problem set 1, we looked at how to solve Poisson's equation. That was sort of our warm-up. Now, problem set 2, what you're going to get to do on there is your first density functional theory calculation, because we've built up all the necessary framework for that. Right now, it's just going to be a demonstration calculation, however, and it's going to be, you're going to look at multiple states in a 3D quantum dot, just as a model to put the method through its paces. But at least you'll have a fully functional DFT code by that point, and that's due this coming Tuesday again. Problem set 3 is where I think things are really going to start to get interesting. In problem set 3, you'll build up enough capability to handle a hydrogen molecule. And you'll have a chance to calculate, what are we going to calculate? The usual stuff, the bond length of the molecule, the binding energy of the molecule, and the vibrational frequency. Right? All based on the simple theory that we can just write down. And it constantly blows my mind, this part of it, but you're just going to calculate the thing, and darn it if it's not going to match the experiment. So it just blows my mind that that's actually possible, but it happens all the time. So that's what you're going to get to do if you stick through till problem set 3, and that'll be due then the following Wednesday. At that point, I'll not be teaching the course anymore, but take you about a week to do that, I think. And then there's a fourth assignment, which given the pace that we've covered the material, we won't have really time, I think, to make it due. You will have all the information needed to code it up, though. So I'm just going to require these first 3, but I just feel like, well, you've got all this technology now, you might as well just finish the thing off if you're interested. If you want to carry out calculations in solids, in particular a germanium solid calculation, we can see the covalent bonds and the cohesive energy and all that. There'll be another problem set I'll put up there if you want to just continue on. And if for some reason you feel a need to make a good impression on me, please, by all means, go ahead. All right, so great. So that's kind of the where we're going with the code. Now for today, our main topic is, at the beginning, is to finish this discussion we've been having of advanced minimization algorithms. And that is basically going to finish the material then that you need to finish the last assignment. On assignment 2, we're just using simplest, steepest descents. That's fine. It's just not efficient enough really to do an interesting problem like the hydrogen molecule. So with the finishing up of the discussion of the advanced minimization algorithms today, you'll have enough power in your code then to actually apply it in problem set 3 to that actual molecule. So I think that'll be a good lot of fun to be able to do that. Then there's a little side topic that we'll take a little detour on for a little while. Also help us understand some of the structure in our algebra a little better. There's a certain subtlety in extracting eigenstates from these calculations. It turns out there's a certain invariance in the density functional theory energy expression which prevents us actually from directly getting the eigenstates out from this minimization. And we'll talk about that subtlety. What it means, though, is that if you want to look at the eigenstates and get the eigenvalues out, you have to do a little bit of a manipulation on the final data, some post-processing once you've done the minimization. That's described, how to do it is actually described in problem set 2, and you actually do that in the coming up problem set. And you're told how to do it, but I thought it'd be nice for you guys to know what you were doing, in addition to how to do it. So we'll take a little 15-minute discussion detour on that. And then, at that point, you basically have everything you need to calculate energies and densities and eigenstates and eigenvalues for whatever system might be of interest to you. So that's nice. Then that pretty much, I guess, would finish up the material for the course up to the first 3 problem sets and give you a complete, coherent picture of practical density functional calculation. But one can always optimize things further, and we have a little bit of time. So I'm going to describe some further optimizations one could make to really tweak up the code. And these actually are necessary to carry out the germanium solid calculation. So these would go on to that 4th assignment. if you're interested in carrying it out. And basically what it's going to boil down to is two different tricks that are going to allow us to save a factor of about 500,000 in the memory requirements for carrying out that germanium solid calculation. So it's quite substantial. You can imagine, we're probably going to need this to get that germanium thing on there if it's going to be 1,000,000 times more than we could handle currently. So that's what the rest of the lecture will finish up on. I'm not sure we'll finish the discussion of both of the optimizations that combine together to give us these savings, but we'll see how far we get today, and then we'll just finish it up in the last lecture, the remaining parts. Okay, so right on into the agenda on the advanced minimization algorithms. If we recall where we had left off last time, I had basically gotten to the point where I'd shown you the overall minimization technique we'll be using, which is preconditioned conjugate gradients to solve generic minimization problems. And my sort of generic statement of the problem is this: I'm minimizing over some column vector of real coefficients of some real function of those coefficients. And the algorithm proceeds as follows. As you recall, you have some initial guess for the solution, and then you proceed iteratively. In the first phase of the iteration, you compute the search direction that you're going to move along to carry out the minimization. And we calculate that by looking at the gradient, pre-treating it a little bit with this preconditioning matrix, which you might remember is a model of the inverse of the Hessian. If we had the exact inverse Hessian here, we'd solve the problem in one step, basically. But we don't. So we have some more machinery involved. So the search direction is that preconditioned gradient, this is called, plus some magic mixture of the previous search direction. And the point of that magic, again, is beyond the scope of this course. It's about a 25-minute discussion. If we have time left over in the last lecture, we'll do it. I don't think we will. Basically, what it accomplishes, again, is that once you've minimized in a certain direction, any further optimizations won't project into the direction that you've done. So as iterations go by, you've solved the problem in successively larger and larger subspaces. Any event, once you've got that search direction, we have to decide how far to go along it. And so we decided that we'll do what's called line minimization, or I like to call it lin-min for short. And basically, what you do is you find the alpha that would minimize the energy just at least along this one search direction that you've picked out. Once you find that ideal alpha, you update the state of your system to that new point, and then you're ready to iterate. That's the overall algorithm. Now this begs two questions. The first is, in particular for us, well, what are we going to use for this K, this preconditioner? And secondly, how do we actually carry out this third step here? How do we actually find the best point along a line? That's inconvenient. Let's see.